The plan for today is to talk about the latent variable models. So just as a recap, what we've seen so far is the first kind of family of generative models, so the autoregressive ones, where the kind of key idea is that we use chain rule to describe a joint probability distribution as a product of conditionals. And then we essentially try to approximate the conditionals using some kind of neural network. And we've seen several options for doing that, including RNNs, CNNs, transformers. At the end of the day, the kind of like the core underlying idea is really this autoregressive factorization of the joint. And we've seen that there is the autoregressive models are good because they give you access to the likelihood. It's relatively easy to evaluate the probability of any data point. You just multiply together the conditionals. And what this means is that you can train them by maximum likelihood. You can, you have a training data set. You can evaluate the probability assigned by your model to the data. And you can optimize the parameters of your probability distribution to maximize the probability of the data set you're given. And you can use the likelihood to do other things, like, for example, anomaly detection. The kind of like the cons of autoregressive models is that, well, first of all, you have to pick an ordering. And sometimes it's straightforward to do it. Sometimes it can be tricky to figure out what is the right ordering that you're going to use to kind of construct the chain rule factorization. Generation is slow. So even if you use an architecture that allows you to compute all the conditionals basically in parallel, like a transformer, the challenge is that at generation, you have to generate basically one variable at a time. And so that can be slow. And another thing is that it's not obvious how you can get features from the data in an unsupervised way. And that, we'll see, is one of the things that we're going to be able to do using latent variable models. And so the plan for today is to start talking about latent variable models. We'll start from simple ones like mixture models, and then we'll start the discussion of the variational autoencoder or the VAE, and we'll see how to do inference and learning when you have latent variables. So the kind of high-level motivation for building or using a latent variable model is that when you're trying to model complicated data set, for example, a data set of images of people like this one, the problem is typically hard because there is a lot of variability that you have to capture. For example, in this case, there might be a lot of variability that depends because people have different age, people have different poses, people have different hair colors, eye colors. And so all these things lead to very different kind of like values for the pixels that you have in the data set. And so the problem is that if you somehow had access to these sort of annotations, perhaps you would be able to do it would be easier to model the distribution because you could sort of like build separate models where you're kind of conditioning on hair color or the eye color or the age or whatever attribute you have access to. But unless you have annotations, all you have access to is a bunch of images. And although you believe that you can kind of see that there is this latent structure, it's not annotated. So it's not obvious how you take advantage of it. And so the idea of latent variable models is to essentially add a bunch of random variables, which we're going to denote Z, which are supposed to capture all these latent factors of variation. So even though we only care about modeling pixels in the images, we're going to incorporate a bunch of other random variables in our model. And we're going to call these random variables latent or hidden because they are not observed in the data set. So we only get to see the pixel values, the X part, but we don't get to see the corresponding values for the latent factors of variation. And by doing this, we get several advantages. We're going to get more flexible, kind of like model families. And if you can sort of like fit a model reasonably well, then we might also be able to kind of extract these latent variables given the pixel values. And if you're doing a good job at modeling these common characteristics that the different data points have, then you might use these features to do other things. You might, try to predict, if you have a classification task, it might be easier to train a model that works at the level of these latent variables as opposed to the direct pixel values. Because often you might be able to, you might need a small number of latent variables to describe a much more high-dimensional kind of data set, like images, for example. So at the high level, sort of like the kind of trying to formalize a little bit this intuition, what we want to do is we want to have a joint probability distribution between the x, which are basically all the pixel values that we have in an image, and these latent variables z. And so here I'm showing the x shaded, meaning that it's observed, and the z variables are white, and they're not shaded because this basically means for every data point we don't get to see, we don't have annotations for the corresponding latent variables. And conceptually, you can think of a sort of like a Bayesian network that might look something like this, right? Where there is the pixel values that you get to see, and then there's a bunch of latent factors of variation that would be helpful in describing the different types of images that you might have access to in your data set. And these latent variables, again, they might correspond to these high-level features. And if z is chosen properly, you get several advantages because it might be a lot easier to model p of x given z as opposed to the marginal distribution p of x. Right? If you somehow are able to cluster the data points and divide them into different groups, then modeling the images that belong to every particular group separately, which is kind of like what this p of x given z would do, could be much easier because at that point there is a lot less variation that you have to capture once you condition on these latent features. And the other good thing that you have access to if you do this is that if then you try to infer the latent variables for a new data point x, then you can sort of like identify these features. And so again, this is sort of like going towards the representation learning angle or the computer vision as inverse graphics. Somehow, if you have a good generative model that can produce images based on a set of latent variables, if you can then infer these latent variables, then you might be discovering feature structure that you can use for different sort of problems. And the problem is that it might be very hard to specify kind of like a graphical model like this and specify all the conditionals. And so as usual, instead of taking the graphical model view or the Bayesian network view that we have here, we're going to try to use deep neural networks to do the work for us. Right? And so what we're going to do instead is we're still going to keep that kind of structure where we have a set of observed variables x and latent variable z, but we're not going to have anything interpretable in terms of like how the random variables are related to each other or what they mean. We're just going to assume that there is a set of random variables z that are somewhat simple. For example, they might be distributed according to a simple Gaussian distribution. And then we model the conditional distribution of x given z, again, using basically some kind of like deep generative model where we have a simple distribution, let's say a Gaussian, but the parameters of this distribution depend on in some potentially complicated way on the latent variables through, let's say, a couple of neural networks, mu theta and sigma theta, that are basically giving us the mean and the standard deviation that we're expecting for x, given that the latent variables take a particular value. And so again, because at this point the latent variables, they don't have any pre-specified semantic, then we're sort of like hoping that by fitting this model, let's say by maximum likelihood, we end up somehow discovering interesting latent structure. And as usual, this is basically, this is an unsupervised learning problem. So it's kind of like ill-defined because what does it mean that the structure is meaningful? What is it that we're actually after here? It's not obvious. But the intuition is that hopefully by trying to model the data using these latent variables, we might discover some interesting structure, some interesting kind of correspondence between X and Z that then would, first of all, make learning easier because we are able to model a distribution of images, X, using something like a Gaussian. And then, by inferring the latent variables given the observed one, given the X, we're hopefully going to discover interesting features that then we can use to analyze the data or to do transfer learning or whatever you want. Question? Can you repeat?
Z, how you manage to update Z, the latent variable, by fitting the neural network?
So the question is how we change Z when we fit the neural network? Yeah, so we'll see how we do learning. That's the challenge. So the challenge is that the Z variables are not observed during training. And so it's not obvious how you should update the parameters of this neural network that gives you essentially the X as a function of Z when you don't know what Z was. And so intuitively, you're going to have to sort of guess what is the value of Z for any given X. And you're going to use some kind of procedure to try to fit this model. So if you've seen EM, it's going to have the flavor of sort of like an EM-like procedure where we're going to try to guess a value for the latent variables, and then we're going to try to fit the model.
So is the image X here, how is that being represented? Is it autoregressively being generated?
The question is X being represented autoregressively? In this case, there is no autoregressive structure. So X given Z is just a Gaussian distribution, so something very simple. The parameters of this Gaussian are determined through this potentially very complicated nonlinear relationship with respect to Z. And as we'll see, even though P of X given Z is very simple, it's just a Gaussian, and you would never expect that a single Gaussian is sufficiently flexible to model anything interesting because you have these latent variables. As we discussed before, if you somehow are able to cluster the data points in a reasonable way, then within the cluster, which is kind of like this, what this object is, you might be able to get away with a very simple kind of distribution. And that's kind of like the idea behind a latent variable model.
In the last lecture, we spoke about how we basically reflect the joint distribution in these individual conditionals and then learn your networks for these individual conditionals, right? Is it common practice that these individual conditionals are modeled with a Gaussian, or are there approaches classical, common approaches where we use different distributions, and also then these models that we have for the mean and the variation, are they is this one model, or for each conditional is a different model?
Yeah. So the question is, is I guess what sort of mu's and z, what kind of functions do we use here, and are they different for every z? In this case, the functions are the same. So there's a single function that is then going to give you different outputs when you fit in different z values. So the functions are fixed. The other question is, well, does it have to be a Gaussian? Not necessarily. You can use an autoregressive model there if you wanted to. Kind of the strategy behind the latent variable model is to usually choose these conditionals to be simple. Because again, you have this clustering kind of behavior, and so you might be able to get away with a simple P of X given Z. But you can certainly, this is sort of the mix and match kind of part of this course, you can get a different kind of generative model by replacing this P of X given Z with an autoregressive model. That gives you even more sort of flexibility. But the story behind the variational autoencoder is to keep that simple.
Maybe I didn't fully understand, but can you kind of clarify the big picture motivation for why we want to model P of X given Z and P of X in this case?
So the goal is, as usual, so the question is, why do we need P of X given Z and P of X? So the goal is to always just model P of X. So that's the same as in the autoregressive model. You want to be able to fit a probability distribution over these X variables, which are the ones you have access to, the pixels, whatever. The motivation for using the Z variable is that Well, one, it might make your life easier in the sense that if you somehow are able to cluster the data using the Z variables, then learning becomes easier. The second one is that being able to infer the latent variables might be useful in itself, because really maybe what you're after is not generating images, but kind of like understanding what sort of latent factors or variations exist in your data set. And so the prior here in this case is very simple, it's just a Gaussian. But yeah, you could have more complicated priors.
How Z can be intuitively thought of as unique features. Over here, is it a way to kind of get a sense of what these learned features are?
Yeah, so that's what I was saying, sort of like that, you just hope that you discover something meaningful. You can certainly test. Once you've trained the model, you can certainly change, let's say, one of the Z variables and see how that affects the images that you generate. And so you can certainly test whether you've discovered something meaningful or not. It might not be, whether you discover something meaningful or not is not guaranteed by the learning objective.
Is the number of latent variables just a hyperparameter that we end up training on?
So the question is, yeah, is the number of latent variables a hyperparameter? Yes.
So in this model, you're learning how to model P of X, and then you're conditioning on Z's, so that you have to control. I'm still confused how are we supposed to sample and then do density estimation on this point?
Yeah, so the question is, if we use this kind of model, how do we sample? How do we do density estimation? So sampling is easy, because what you do is you first sample. This is you can think of it as an autoregressive model over two groups of variables, the Z's and the X's. And so what you would do is you would first choose a latent factor of variation. So you sample Z from a Gaussian, which we know how to do, it's trivial. Then you feed Z through these two neural networks, and you get a mean and a covariance matrix. Then that defines another Gaussian. Then you sample from that Gaussian. So sampling is very easy. Evaluating P of X, as we'll see, that's the challenge. That's kind of like the no free lunch part. Everything seems great, except that evaluating P of X, which is kind of doing density estimation, becomes hard. And that's kind of like what's going to come up next. Yeah.
This does not seem like end-to-end differentiable, right?
Yeah, so the question is this end-to-end differentiable? How do we train it? Yeah, that's going to be the topic of this lecture. Yeah. All right, so let's see first as a warm-up the kind of like the simplest kind of latent variable model that you can think of, which you might have seen before. That's the mixture of Gaussians, right? So again, we have this simple Bayes net Z pointing to X, and you can think of a mixture of Gaussian as being a shallow latent variable model where there is no deep neural network involved. In this case, Z is just a categorical random variable, which determines the mixture component. Let's say there is K mixtures here. And then P of X given Z, again, is a Gaussian. And then you have some kind of lookup table here that would tell you what is the mean and what is the covariance for mixture component K. There's K mixtures, and so you have K means and K covariances, and that defines a generative model. So to sample, again, you would sample first a mixture component, a Z, and then you would sample X from a Gaussian with the corresponding mean and covariance. And so it would look something like this. So if X is two-dimensional, so there is X1 and X2, then each of these Gaussians would be a two-dimensional Gaussian, and these Gaussians will have different means, say mu1, mu2, and mu3. They will have different covariances. And so it might look something like this. And so the generative process, again, is you pick a component, and then you sample a data point from that Gaussian. So maybe you uniformly pick, or whatever is the prior over Z. Maybe you sample K, you can sample Z, you get 2, and then you have to pick a point distributed according to a Gaussian with mean here and covariance shaped like that, and so forth. This is useful, again, kind of like if you think about the clustering interpretation, you can think of this kind of model as giving you one way of performing clustering or which is sort of like a basic kind of unsupervised learning task. This is an example where you have a data set collected for the Old Faithful geyser in Yellowstone National Park, and then each data point here corresponds to an eruption of the geyser. And then you can see there's two features here, the duration of the eruption and the time between two eruptions. And the data set looks like this. So you can see there's some kind of relationship between these two things. And the larger the interval between two eruptions, the longer than the following eruption is. And you could try to model this using a single Gaussian. If you fit the parameters, it's going to look like this. You're going to put the mean here, and you're going to choose a covariance that kind of like captures that correlation between the features. And you can see it's not doing a great job. Like you're putting a lot of probability mass here where there is no actual data. But that's sort of like the best you can do if you're forced to pick a Gaussian as your model. But if you look at the data, it kind of looks like there is two types of eruptions. There is type 1 that behaves like this, and type 2 that behaves like this. And so you're going to get a much better fit to the data if you have two Gaussians, a mixture of two Gaussians that are kind of like look like that. And if you can somehow fit this model automatically, then by inferring the z variable given the x, figuring out if a point belongs to the blue or the red mixture, you can kind of like identify which type of eruption you're dealing with. So again, this is sort of like this idea of identifying features based on the observed data. And again, you can see that this is kind of ill-posed because it's unsupervised learning, and we're hoping to discover some meaningful structure, but it's not clear that this is always possible. It's not clear what it means to find good structure, or what's a good clustering, right? You might have different definitions of what a good clustering is, and this will give you a clustering. Whether it is the one that you want or the best one is not guaranteed. And so, yeah, you can imagine that you can use it to do unsupervised learning. You can have, if you have more mixture components, you have a data set that looks like this, then you might want to model it, let's say, using a mixture of three Gaussians. And again, kind of like identifying the mixture component, which is the color here, would tell you sort of like which component the data point is coming from, and it tells you something about how to cluster the data points in different ways.
Would it be reasonable to guess that this would fail very hard on like image classification?
So the question is, yeah, will this fail very hard on image? Probably. You wouldn't expect, unless K is extremely large. If you have, like, say, a mixture of two Gaussians, then you would, let's say if you have a single Gaussian, then you would kind of like choose the mean to be the mean of all the images, and then you put some kind of standard deviation, and you can imagine you're going to get a blob. It's not going to be very good. Even if you are able to divide your training set into two groups and fit two separate Gaussians, still not going to work very well. If K becomes extremely large, in theory, you can approximate anything, so eventually it would work. But yeah, in practice, it would require a K that is extremely large. Cool. And here is actually an example on image data. Again, this is on MNIST, and this is the kind of like latent space Z. This is a projection of that, but you can kind of like imagine that one axis is Z1, another axis is Z2, and then you take your MNIST data set, and then you kind of like try to figure out where it lands in Z, each data point, where it lands in Z space. And you can kind of see that, again, it's able to do some reasonable clustering in the sense that data points that actually belong to the same class, which was not known to the generative model. For example, red points here corresponds to digits 2, and you can see that they are kind of like all grouped together. They all have similar Z values after training this model. And so, there's not a single cluster here for the 2s. There is kind of 2 of them. Maybe the points in this cluster have a slightly different style than the points in this cluster. I mean, it's hard to say exactly what the clustering is doing here. And again, it hints at the fact that unsupervised learning is hard, but this is sort of like the intuition for what you might hope to get if you try to do this on an image data set, you might hope to be able to discover different classes, you might be able to different styles, and you're hoping to discover that automatically by fitting a latent variable model and just looking at the kind of Z's that you discover.
Explain it more for both the like shallow and the deep variable model, how you actually learn these posteriors.
Yeah, so the question is how do you learn them, and I haven't talked about it. It's going to be that we're gonna go through that, yeah, in this lecture.
The model before doing the dimensionality reduction into 2 dimensions, and then you plotted things, but it actually looks better. Like it looks like it would make more sense if you did the dimensionality reduction first and then tried to learn a mixture of Gaussians. Like it looks more like it could be expressed that way.
So there is no mixture of Gaussians learned here. So this is sort of like showing this is more like the results of training a deep generative models where the Z's are actually not even categorical. Like the Z's variables here are more like Gaussian or like real valued. And so what I'm plotting here is for each data point, what is the corresponding inferred value of Z, which is no longer a number. It's kind of like a point in this 2-dimensional space. And it just so happened that it's finding something reasonable. But again, it's not guaranteed. Yeah.
So when we start sampling from a VAE, we normalize it to like a mean and standard deviation of 0.1. But in this case, if we can do a dimensionality reduction, we then fit a model on this to then have a PFZ to sample from this, not normal.
Yeah. So I think the question is whether, I guess in the model I had here, the P of Z was a simple distribution like a Gaussian. And perhaps if you look at this latent space, for example, which is actually not a VAE, I think, but then that's why it might not look like a Gaussian. It has a bunch of holes, and so you might be better off having a mixture of Gaussians, for example, for P of Z. And you might actually try to learn the P of Z as part of the model, and you can certainly do that. Cool. So an alternative motivation is that it's a very powerful way of combining simple models and get a more expressive one out. Like using latent variables allows you to have this kind of mixture model behavior, which is a very good way of building very flexible kind of like generative models. And you can kind of see in the example of the mixture of Gaussian. If you have 3 Gaussians, a blue, an orange, and a green one, and you can see they have different means and different standard deviations, so they have all these bell curves. If you think about the corresponding marginal distribution over X, has this very interesting red shape. So even though each of the individual components is pretty simple, it's just a bell curve, and there's not too much you can do about changing the shape of that function. The moment you start mixing them together, you can get much more interesting shapes for the probability density that you get. And the reason is that when you want to evaluate the probability under this mixture model, the probability of a data point X, what is that object? Well, it's the marginal. You basically need to say, what was the probability of generating that point under the blue curve, plus the probability of generating that point under the orange curve, and plus the probability under the green curve. And this is just the definition of the marginal probability. You marginalize out the Z. In this case, the joint is just something that looks like this, where P of Z is just a categorical distribution, and the P of X given Z is again something very simple, just a Gaussian, with different means and different standard deviations. And so you can see that even though the components, the P of X given Z are super simple, just Gaussians, the marginal that you get is much more interesting in terms of the shape that you can get. And that's sort of like the one way to think about why these variational autoencoders are so powerful, because it's basically the same thing, except that now you don't have a finite number of mixture components. So the Z variable is no longer a categorical random variable, 1, 2, 3, 4, 5K. Now Z can take an infinite number of different values. There is a Gaussian distribution that you sample Z from. So there is essentially, you can think of it as an infinite number of mixture components. So even though P of X given Z is again Gaussian, now we have a mixture of an infinite number of Gaussians. And what we're giving up is that sort of like in this Gaussian mixture model case, we were able to choose the mean and the standard deviations of these Gaussians any way we wanted, because you basically have a lookup table, and so you have complete flexibility in choosing the mean and the standard deviation of the Gaussians. In the VAE world, the means and the standard deviations of all these Gaussians are not arbitrary. They are chosen by feeding Z through this neural network, through two neural networks, let's say mu and sigma, that will basically give you the mean and the standard deviation for that Gaussian component. There's no longer a lookup table. Now it's whatever you can describe using a neural network.
Sorry, can you describe again how this is different from before? And then first of all, you said the number of Gaussians. Are you saying that the number of needed variables?
So there's still, basically Z can take an infinite number of values because Z is continuous. Before it could only take K different values, yeah.
Like uniform distribution to sample Z.
The question is, yeah, can't we just use a uniform distribution? Yeah, you can. This is just, I'm just showing a Gaussian, but yeah, uniform distribution would work as well. Yeah.
You said Z is the input to the neural network. Does that mean we first sample from Z and then input into the neural network?
To sample, yeah, the process to sample it would be the same as before. Like in the Gaussian mixture model, you pick a component, sample a value of Z, then you do your lookup, you get the mean, the standard deviation, and then you sample from the Gaussian. The sampling process here is the same. You sample a Z, now it's a Gaussian, then you feed it through the two neural networks to get the means and the standard deviations of the corresponding Gaussian, and then you sample from P of X given Z. So you sample from a Gaussian with that mean and that standard deviation.
A little confused about why the mixture makes sense. Like, let's say you have a unique cluster corresponding to 6 and another corresponding to 7, and now you're creating a mixture that's halfway in between. But in reality, there's probably no digit that's halfway between 6 and 7, right? So why does this work better in practice?
What does it work better than the finite mixture component? Yeah, so I mean, the question is, would you want Z to be discrete, I guess, or continuous? And if you're trying to model kind of like discrete sort of clusters, is this the right way of doing things? And yeah, you're right. That's sort of like here Z is continuous, so you have some way of transitioning between the clusters, which might or might not make sense, and it might need to find strange kind of axis of variation to make that happen. You can also have a mixture of discrete and continuous. Like this is the setting that a VAE uses, and it tends to work well in practice.
To back off of that, what does it mean intuitively to have like an infinite number of clusters?
Well, I mean, intuitively, it just means that Z is no longer a categorical random variable, so there's not a finite number of choices that you can make, but it's more like what I had here, where the Z variables can take values in this 2D space, and so there's not really even necessarily a notion of, well, you have to pick either here or here. You can kind of like be in between.
It's like a point in between like 6 and 1 would be like 3.2.
Yes, yeah, exactly.
Yeah, since Z is described by like a Gaussian distribution, does that mean like its mean is like some average of possible latent variables or something that of all the x's?
Could you repeat the question?
Yeah, can you interpret like the mean of Z as like some average latent representation of all of the data x?
Yeah, in some sense, yes. And then usually the average is 0, so you're basically forcing the average of all the latent representations of the data points to be centered at 0. So yeah. I mean, it depends on the training objective, but using the training objective that we will see in this lecture, yes, that would be the effect. Yeah.
When you had a categorical representation for Z, for the distribution, was it like a uniform probability across the categories?
Yeah, the question is, does Z, in a mixture of Gaussians, does Z have to be a uniform distribution? It doesn't have to. No, you can have.
How it works for Z to be a normal distribution here, or like versus a uniform, or how you're choosing Z to be a normal distribution.
Yeah, so that's kind of like to some extent an arbitrary choice. Like you can choose other priors kind of like the key insight is that it just has to be something simple that you're going to sample from efficiently. The conditional, the P of X given Z, also something simple. Here I'm using a Gaussian, but you'd use a logistic, like a factorized logistic, or it can be anything as long as it's simple. And all the complexity is really in these neural networks that would figure out how to map the parameter, how to map the latent variable to the parameters of this simple distribution. And you're going to get different results depending on the choices you make. This is sort of like the simplest Gaussian and Gaussian. But yeah.
In a GMM, do we have a neural network for each value of Z, or do we have just a single neural network that we're training? One for the mean, one for the standard deviation.
So in a GMM, there's no neural network. It's just a lookup. So it's the most flexible kind of mapping you can think of because you're allowed to choose any value you want for the different values that Z can take. So it's kind of like more like a Bayesian network world where you're allowed, it's a lookup table, which is great because it's super flexible. It's bad because it doesn't scale the moment you have many. How to fit it? Yeah, we'll see that soon.
So just to clarify, are we going to update the prior Z while we are fitting the model?
You could, in this world, I'm assuming that the prior is fixed. There is no learnable parameter. As usual, the learnable parameters are the theta, which in this case would be the parameters of these two neural networks. So you might have a very simple, a very shallow linear neural network where to get the mean, you just take a linear combination of the Z variables and then you apply some nonlinearity. And then, similarly, another simple neural network that would give you the parameters of the covariance matrix. Perhaps you can make a diagonal, something like this.
I just want to clarify the intuition. So in the mixture, you're saying you're summing over a bunch of normals. Switching over here, you're saying you can represent that sum as a single normal, and you're directly predicting the mean and variance for that normal to the matrices.
So the marginal, let's see if I have it. So the marginal basically becomes an integral. So instead of being a sum over all possible values of Z, you have an integral over all the possible values that Z can take. But it's the same machinery. Yeah.
In practice, is the dimension of Z much lower or much higher than X?
Good question, yeah. So what is the dimension of Z in practice? Typically, the dimension of Z would be much lower than the dimensionality of X. And the hope is that, yeah, you might discover a small number of latent factors of variation that describe sort of your data. I'll train it, yeah, we'll talk about it soon, yeah.
Does it even make sense for Z to be greater than, like the dimensionality of Z to be greater than X?
So we'll see another kind of generative model that will basically be identical to this, except that Z will have exactly the same dimensionality of X. And that's, for example, what a diffusion model does. So you might not necessarily always want to reduce the dimensionality. Having the same dimensionality will allow you to have sort of nice computational properties. Yeah.
Is it possible to have a more put more information into the prior as opposed to just sampling from standard deviation?
Yes, you can certainly put more information, and I think there are two ways to think about it. One is if the prior is more complex, like instead of having a Gaussian, you can put an autoregressive model over the latent variables. You're going to get an even more flexible kind of distribution. The other way to do it would be if you already have some prior knowledge about the types of, maybe you know that there is a bunch of classes, there's 1,000 classes or 10 classes, then maybe you want to have one categorical random variable. And so if you have some prior over what kind of latent factors of variation you expect to exist in the data, you can try to capture that by choosing suitable priors.
So in your shallow latent variable models, your number of Gaussians is equal to k, right? Here, since this is a normal distribution, your number of k is less.
Yeah, exactly. Cool. So what you would do then is you would somehow try to fit this model to data. And in this case, the parameters that you can choose are all these neural network, the parameters of these two neural networks, mu and sigma. And again, the takeaway is the same as the Gaussian mixture model. Even though P of X given Z is super simple, it's just a Gaussian, the marginal that you get over the x variables is very flexible. It's kind of like a big mixture model. And so that's kind of like the recap. Two kind of ways to think about it. One is to define complicated marginals in terms of simple conditionals. And then this idea of using the latent variables to kind of like cluster data points. And again, sort of like being able to model them through relatively simple conditionals once you've clustered them.
On the previous slide, for our covariance matrix, why are we exponentiating the output of that generator?
Oh, just because it has to be positive semi-definite.
And we're just modeling it as a diagonal.
Yeah, which is again a modeling choice, but you could make it non-diagonal. Yeah. Cool. And now we'll see the no-free lunch part, which is going to be much harder to learn these models compared to autoregressive, fully observed kind of models that we've seen so far. And the problem is that basically you have missing values. And so kind of like what happens is something like this. Like imagine that you still want to train an autoregressive model, but now some of your data is missing. So you still want to fit an autoregressive model over the pixel values, but now you don't know the value of the top half of the images. So what do you need to do? Well, there is two sets of variables here again. There is the part that you get to see, and then there is some part that you don't get to see that is latent. And then there is a joint distribution. So your pixel CNN would tell you the relationship between the x variables and the z variables. So you can choose, you can complete the green part, the missing part any way you want. And let's say your autoregressive model will tell you how likely the full image is, because you have a joint distribution over z and x. The challenge is that you only get to see the observed part, so you only get to see the x part. And so you need to be able to evaluate what is the probability of observing, let's say, this bottom half of a digit. And in order to do that, again, we have to marginalize. So you have to basically look at all possible ways of completing that image, and you have to sum the probabilities of all these possible completions. And even though the joint is easy to evaluate, because maybe it's just a product of conditionals, or like in the VAE case, it's just the product of two Gaussians, basically, you have this mixture in behavior. Just like in the mixture of Gaussian, when you want to evaluate the probability over just the x part, you have to sum out all the things, over all possible values of the unobserved variables. So you have to look at all possible completions, and you have to check how likely the different completions are, and you sum them up. Just like in the mixture of Gaussian case, you need to sum the probability under each mixture component. The same thing. And the problem is that there is potentially too many possible completions. Like in the mixture of Gaussian case, maybe you only have k possible values that the z variable can take, and so this thing is easy to evaluate. You can just brute force it. But if you have a high-dimensional kind of like latent variable z, this sum can be extremely expensive to evaluate. So you get flexibility because you're mixturing a lot of distributions, but then you pay a price because it's hard to evaluate that quantity.
Possible to evaluate it? Because that's how we don't know those things. So how would you sum over this?
Well, you sum over all possible completions. So you would have to put all white pixels, and then you check how likely is that, probably very low. Then you try all black pixels, and then you would try all possible combinations, and then you check the probability of each one of them, and you sum them up.
Instead of having the z to be the full completion, can the z just be like some digit, like the true digit? I mean, assume I know the true digit, that's a 9 or that's a 6 or something.
Yeah. In that case, you would have a latent variable that is maybe categorical, and that's what you would do, if you're trying to infer kind of like the digit identity. Cool. And in a variational autoencoder, you have the same thing. The z's are not observed at training time. So at training time, you only get to see the x part. So when you want to evaluate the probability of observing a particular x, you kind of have to go through all possible values that the z variables can take, and you have to figure out how likely was I to generate that particular x. And the z variable is not even discrete, so if you want to evaluate the probability of generating a particular x, you have to actually integrate over all possible values that the z variables can take. So you have to go through all possible choices of the z variable. You have to see where it would map to. You would check the probability under that Gaussian mixture component, and then you integrate the map. Again, you can imagine that this is super expensive because, yeah, especially if you have a reasonable number of latent variables, a curse of dimensionality, this is very expensive to even numerically approximate this kind of integral. But that's where the flexibility comes from, right? You're integrating over an infinite number of mixture components.
Like for each z, would I just calculate the probability of x plus z?
Yeah, so for every z, you can evaluate the joint. Just like here, for every value of z, and I can evaluate p of x comma z. Like I can just check the z, I map it through the neural networks, I get a Gaussian, I can evaluate the probabilities. But because I don't know what was the z corresponding to that data point, right? The z is not observed, so I have to kind of try all of them. Just like here, kind of like I only get to see the bottom part. I don't know what was the top part for the particular image. I have to guess. I have to try every possible way of completing that data point, and I have to sum them up.
Possibility of z, right?
Of the z's, yeah.
How does
Not the x.
How does all possibility of z relate to computing all possibilities? Why did this?
In this case, I'm assuming that the z variables represent the top part, the unobserved part. Yeah. Cool. So that's sort of like the challenge, evaluating this marginal probability over x. You need to integrate over all the possible values of the z variables. And so kind of like that's the setting. You have a joint distribution over x and z. Yeah.
Observing x bar. So you know what x bar is, and you want to predict like what is the most likely thing that should be over there. Then you also have to go through every single possible x value. So like over here, you're looking at the probability of x equals x bar, and now you have to loop over all possibilities.
Yeah.
But what if you don't actually know that the training data point is x bar, and you want to actually solve that?
So that can also work. So the setting that we're going to consider is one where in the data set, the x variables are always observed. You could also think about a setting where you have some missing data, and some of the x variables are missing themselves. You have it through. Yeah.
So in the previous slide, the capital Z is the same as the normal distribution, the prime.
Yeah.
Okay. So we have to so instead of summation, we have integral now. How are we supposed to compute the integral? Like, do we sample infinitely or like?
Yeah. So we'll see how to compute it. So that's kind of like the setting. We have a data set, but for every data point, we only get to see the x variables, and the z variables are missing. They are unobserved. And then, so you can think of the data set as being a collection, let's say, of images, x1 through xn. And what we would like to do is we would like to still do maximum likelihood learning. So we would still like to try to find a choice of parameters that maximize the probability of basically generating that particular data set. It's the same objective that we had before. Let's try to find theta that maximizes the probability of the data, maximum likelihood estimation. And or equivalently, the average log likelihood of the data points if you apply a log. And the problem is that evaluating the probability of a data point under this mixture model is expensive because you have to sum over the all possible values that the z variable can take for that data point. And so evaluating this quantity can be intractable. And just as an example, say that you have 30 binary latent variables. Then that sum involves 2 to the 30 terms. So it's just way too expensive to compute this thing. So if the z variables can only take k different values, like a Gaussian mixture model, you can do it, you can brute force it. But if you have many latent variables, you cannot evaluate that quantity efficiently. And for continuous variables, you have an integral instead, which again is tricky to evaluate. And if you are hoping that maybe we only need gradients, because at the end of the day, we just care about optimizing, gradients are also expensive to compute. So trying to do gradient ascent on that quantity is not feasible directly. So we need some kind of approximations, and it has to be very cheap, because think about it, you need to be able to go over the data set many times, and you need to be able to evaluate the gradient for every data point, possibly many times. And so this approximation here has to be very cheap. And the one natural way to try would be to try to do Monte Carlo kind of thing, right? Basically, this quantity would require us to sum over all possible values of z, and instead we could try to just sample a few and get an approximation. And that's the usual recipe that we've seen in the last lecture. The idea is that you can, we have a sum that we're trying to compute. We can try to rewrite that sum as an expectation, essentially. So we can, if there are capital Z, basically possible values that these Z variables can take, we can multiply and divide by the total number of entries in this sum. And then this object here becomes an expectation with respect to a uniform distribution. And now we can apply Monte Carlo. Whenever you have an expectation, you can approximate it with a sample average. So you could say, let's approximate this sum with a sample average. So essentially, you would randomly sample a bunch of values of z, and then you would approximate the expectation with the sample average. You check how likely these completions are under the joint, and then you rescale appropriately. And this would be cheap because you just need to check k completions instead of all the possible completions that you would have to deal with. Yeah.
Is the z is an element of squiggly z? Is that just a subset of all possible values of z? Or what?
That would be all possible values of z. Yeah. It's just I need a set. We're sampling, yeah. So we sample uniformly at random, and then we rescale.
And this is more tractable from what we were doing before, because now we're sampling a discrete number of values.
And a small number. That's the key thing. You just k of them. Could be 1. The cheapest way is to choose k1 here. You just sample 1. You look at the joint likelihood of that completion, and then you rescale appropriately. And that would be a valid estimator for the quantity of interest.
Yeah.
Over here, you're sampling from the uniform Z. I think when we did Monte Carlo last class, we were sampling from the probability distribution of Z. So is there a reason why we treat every Z as equally likely here, whereas before?
Yeah, it's just because we have a sum. So it's so if you can see, I'm multiplying and divided by the total number of things, so that then this becomes an expectation with respect to a uniform distribution. That's the trick, basically.
Z1's 5 times more likely than Z.
That's the problem. That's why this is not going to work, basically. Yeah.
Just trying to understand the rationale of trying to sample the z from the uniform distribution. Is it because we knew that we're never going to see the z, so we kind of gave up on that. So we just do the uniform, which is like almost no priors or something.
Yeah.
Like
so
that.
this is not going to be I mean, you are getting at why this is not a great solution. This is kind of the first attempt doing things uniformly. It's cheap. It's unbiased, but it's not going to work in practice because kind of like what you're suggesting is that if you think about randomly guessing, z's, most likely you're not going to hit the values of z's that have enough kind of like probability under the joint. And so most of the completions that you guess by choosing uniformly random don't make sense. So they would have a very low value of p theta. And so although this, technically speaking, is an unbiased estimator, the variance would be so big that it's not going to work in practice. So somehow, as you kind of like, I think you were suggesting, we need to a smarter way of selecting these latent variables. We don't want to sample uniformly. We want to sample them, trying to guess the ones that make sense, kind of.
Sorry, this is kind of like a big picture question, but when we started off, you were describing Z as important features, of which I think, like, when we tend to think of features, like a person can have eye color and also hair color, but I feel like the way that we've been treating Z so far has been as like a class or like membership in a group. So like, for example, even in the variational autoencoder case, it's like you choose one scalar value. It's between 0 and 1, but it's like one value. Are we just like not there yet in terms of like different model architectures will get to the feature representation, or is there a connection there?
Yeah, so the question, I mean, I think it's a great question, and it's, what these Z's would even end up representing. And well, there is a first question of whether they are discrete or continuous. And that depends on just how you model them. It doesn't matter too much. Whether they end up representing the things that matter, like the hair color or the eye color, it's questionable, right? Right here, we're just saying we just try to do maximum likelihood. We just try to fit the data as well as we can. And we're going to try to use these latent variables to fit the data. That's what the model is going to try to do if you use this objective. Whether you end up with something meaningful or not is not necessarily guaranteed. You end up with some latent variables, such that if you sample from them and you fit them through this model, you get hopefully good images or good a distribution that is very similar to the one in the training set, which means that these latent variables do capture the important latent factors of variation in the data. Whether they correspond to something semantically meaningful, it's is absolutely not guaranteed. Does that answer your question, or?
Not really, but I'll keep listening.
Ask again. I'm sure somebody else has the same question here too. So.
Oh, you wanted me to say it again?
Sure. Yeah.
Sorry to take up everyone's time. I guess just the idea is like, even with the variational autoencoder, we're sampling Z from a distribution, but then ultimately Z is like one scalar value, correct?
Yeah.
But I feel like so for example, with the MNIST, it was like, maybe just to go back to the categorical Z model, you sample like which digit it is you're trying to represent, and then that gives you some Gaussian distribution. But like, if it's something like a picture of someone, it's not the case that there's only one like class they fall into. There are many features which can coexist. So like, somebody can have blue eyes and black hair, somebody can have brown eyes and black hair. Like, how are we representing that here, or are we not representing that yet?
We are to some extent, except up to the fact that they're not going to be necessarily meaningful, but we are using multiple latent factors of variation. So every X will basically be mapped. There is many different, there is many different Z's that could generate that particular X. There is some that are more likely than others. Given X, when you try to infer P of Z given X, you're kind of like guessing what are the latent features for this particular data point. And if you look at what you get, indeed, you end up with soft kind of, if the Z variables are continuous, then you don't end up with a discrete kind of clustering thing. You end up with two values. You end up with 0.5, 0.5. Like these yellow points end up being having Z1 around 0.5, 0.5. It doesn't have a specific meaning, except that all the points that correspond to that class, the digit, end up having similar values of the Z variables.
And then Tim, now trying to answer the question. So if my understanding is correct, the Z we're dealing with right now does not have to be a scalar. It can be a magic factor with multiple values. So like the vector, the first element of the z vector, if it makes sense, it could be like the third color, the second one could be the I color. There's a combination of multiple features, each z, right?
Yes, there could be multiple z's. Yeah. So there's not a single z. There's multiple z's. Like in this case, there's two. There's z1 and z2, and they capture two kind of salient factors of variation.
Combinatorially many.
Yes, that's the problem. Yeah. If you have kind of like what I have here, if you have the 30 binary features binary latent features, they can all be just 0, 1. Then you have 2 to the 30 basically different possible cluster assignments, and then you can't sum them up. Basically, that's the problem. Yeah.
The semantic meaning of disease, can you do anything to like increase like whether they're independent or you're not placed in parameters?
Yeah, so if you try to, there is a whole field of like disentangled representation learning where people have been trying many different ways of trying to come up with models where the latent variables are more meaningful. There are unfortunately theorems showing that it's impossible to do it in general. Practically, people have been able to get reasonable results, but there are some fundamental limitations to what you can do because the problem is essentially ill-posed. Disentangled representation.
Think about example when we have 30 binary latent features, so we have 30 Z's. So do we say that this 30 Z's follows a normal distribution, or like each of the Z follows a normal distribution?
So in this, if the Z's are discrete, then they wouldn't be normal. It would be, I don't know, like each one of them can come from a simple Bernoulli distribution. If Z could be a Gaussian random vector, in which case you would have the integral. Both cases are pretty hard, basically. Yeah.
Also, like big picture questions. So if we're having the data set that have the labels, can I say we just, because here like we're sort of using these latent variables, try to make it easier to compute the marginal distributions, right? So I was just trying to think of just the connections.
Yeah, so I guess there are two answers there. Like if sometimes you get to see the Z values, maybe you have an annotator willing to label these things for you, you can basically, you can imagine that it's not hard to modify this learning objective where, when you know the value of that variable, you don't sum over it, you just plug in the true value. And so you can do some kind of semi-supervised learning where sometimes this variable is observed and sometimes it's not.
Or unsupervised learning manner.
Yes, this is pure, but it's very easy to adjust to the settings. Yes. Sometimes the Z variables are observed. It's the same thing, except the notation becomes ugly because then you have some points where you have it, some you don't, but it's...
Learn some latent variables that have semantic meanings, or they could not, they just, right?
But if you have labels, that's a good way to kind of steer them in the direction that you want. Cool, so, okay, so this was the vanilla kind of setting where you could just try a bunch of, bunch of choices for the random variable at random and hope that you get something, but this is not quite going to work. And so we need a better way of guessing the latent variables for each data point. And so the way to do it is using something called importance sampling, where instead of sampling uniformly at random, we're going to try to sample the important completions more often. So recall, this is the object we want. It's this marginal probability where you have to sum over all possible values of the latent variables. And now what we can do is we can multiply and divide by this Q of Z, where Q is an arbitrary distribution that you can use to choose completions, to choose values for the latent variables. And this is 1, so you can multiplying and divided by Q is fine. And now again, we're back to the setting where we have an expectation with respect to Q of this ratio of probabilities, the probability under the true model and the probability under this proposal distribution, or this way that you're using to guess the completion for the latent variables. And now what we can do again is just Monte Carlo. Again, I mean, this is still an expectation. It's still intractable in general, but we can try to do the usual trick of let's sample a bunch of z's. Now we don't sample them uniformly. We sample them according to this proposal distribution Q, which can be anything you want. And then we approximate the expectation with this sample average, just like before. Now the sample average has this weight, importance weight that you have to account for in the denominator, because the expression inside the expectation has this Q in the denominator, so we have to put it here.
Is Q just something that we're modeling?
So we'll see how to choose Q. For now, this works regardless of how you choose Q. I think what's a good choice for Q? Like intuitively, you want to put probability mass on the z's that are likely under the joint distribution. You'd like to somehow be able to sample the z's that make sense. So you have a current joint distribution between x and z, and you want to choose the z's that make sense, that are the completions that are consistent with what you observe.
So then you're not just sampling from Z, like ideally you want to sample from Z given X.
So this is for a particular data point. So I'm doing it for a single X. You're perfectly right that this choice of Q has to depend on the X, on what you see. But for now, this is a single data point, so I can just have a single Q. That should be supposed to work. And regardless, basically, of how you choose Q, this is an unbiased estimator, meaning that even if you choose a single sample, we know this is the expected value of the sample average is the object we want. So, or equivalently, if you want to think about it, you could say if you were to repeat this experiment a very large number of times and average the results, you will get the true value. So this is a reasonable kind of estimator. Now, the issue is that, the slight issue is that what we care about is not the probability of a data point, but we care about the log probability of a data point. Recall that what we care about is optimize the average log likelihood of the data points. So we need to apply a log to this expression. So we could try to just apply a log on both sides of this equation and get this kind of estimate for the log likelihood. But there is a problem. So for example, if you were to choose a single sample, so if k here is 1, so you just sample a single possible completion, and then you evaluate that estimator that way. So it's just the ratio of the two probabilities. You can kind of see that this is no longer unbiased. The expectation of the log is not the same as the log of the expectation. So if you take an expectation of this object here, like even though the expectation of the right-hand side here is what we want, when you apply a log, there is bias. And that's sort of like we can actually figure out what that bias is. So recall that what we want is this. We want the log marginal probability, which we can write down as this importance sampling kind of distribution. And we know that the log is a concave function, which means that if you have 2 points, x and x prime, and you take a combination of the two and you evaluate the log, this is above the linear combination of the two values of the function. And what this means is that if you, because of this concavity property, we can basically work out what happens if we swap the order of logarithm and expectation. So if we put the expectation outside of the log, we're going to get a bound on the quantity that we want. So there is this thing called Jensen's inequality, which basically says that the logarithm of the expectation of some function, any function, which is just this quantity here, is at least as large as the expectation of the log. And kind of like the picture is, again, you have a log, which is a concave function. And so if you have 2 points, fz1 and fz2, and you take the linear combination of that, you're always below what you would get if you were to apply the log. And so in our world, what this means is that for this particular choice of f of z, which is what we have here, this density ratio, the log of the estimator is at least as large as the average of the log. So what we have here, if we do this, is a lower bound on the object that we want. So on the left, we have the thing we want, which is the log marginal probability of a data point. And on the right, we have a quantity which we can estimate. We take a bunch of samples from Q, and we evaluate this log as a lower bound. Which is not bad, because what this means is that if we were to optimize the quantity on the right, the thing we care about would also kind of like go up, hopefully. It has to be at least as large as whatever we find by optimizing the quantity on the right.
Could you explain to me one more time why we care about the log of this and not the quantity itself?
Yeah, because if you recall, what we want to do is we care about doing maximum likelihood. And so what we care about is, where do I have it? What we care about is this. So we want to go through all the data points, and for every data point, we want to evaluate the log probability of that data point. And so that's the quantity that we'd like to take gradients of, and would like to optimize. And the good news is that we can get a lower bound on that quantity through this machinery. Where is it? I think here. And then the strategy is basically going to be, let's try to optimize this lower bound. And what we will see soon is that the choice of Q, the way you decide how to sample the latent variables, basically controls how tight this lower bound is. So if you have a good choice for Q, then the lower bound is tight, and this basically becomes a very good approximation to the quantity we actually care about, which is the log marginal probability.
Wait, what's stopping us from taking the sample average of the logarithms of the P fit and of the Q?
That's what we're going to do. Yeah. So this one is easy to evaluate. Yeah. That's the right hand side. That's what we're going to actually optimize.
Oh, okay.
The left hand side is what we want. Is exactly the log marginal probability. The right hand side is the thing we can actually easily evaluate. Just sample a bunch of Qs and then get this log density ratio.
So whether this method works or not depends on how well we choose Q log C?
Yes. So, and this thing that you see on the right is something you might have seen, you might have heard before, is the evidence lower bound. The ELBO, which is a lower bound on the probability of evidence, which is basically the probability of X. So X is the evidence, X is the thing you get to see, is the observed part. The probability, the log probability of evidence is the thing you would like to optimize, but it's tricky to evaluate that, and so instead we have this evidence lower bound, the ELBO, which is the thing we can actually compute and optimize.
Can you remind me again why we need density quality here? Is it because the initial function we have is not something that we can very easily compute the minimum of?
Yeah. So the original thing that you would like to have is is this, which is still tricky. You could try to. The expectation itself is not something you can evaluate. So you would have to do a sample average. And you can do the sample average inside or outside. If you kind of like do the simplest case where, let's say you choose k equals 1, then you see that you basically end up, which would be the cheapest way of doing things, where you take a single sample. This is what people would do in practice. Then you see that if you take the expectation of that, you end up with the expectation of the log instead of the log of the expectation.
So it's not a correct approximation?
It's a bound, it's an approximation. It happens to be a decent one because it's a lower bound. And so it's not gonna hurt us too much. You're optimizing a lower bound. If you maximize the lower bound, the true quantity is always gonna be above, and so it's also gonna go up.
Yeah, so what you're saying is that if we sample from here, we just end up getting a log of the expectation, which is not what we want. So instead we can use Jensen's inequality to describe the function as the expectation of a log, and we can solve for whatever its minimum is and value the minimum of the other function as well.
So Jensen's inequality basically just tells you what happens if you were to do this approximation, where you take the expectation and then the log.
So now we can just find the middle of one of these functions instead of one.
But maximize. We're actually maximizing here, and we can maximize. This one is easy to do.
Which is the same as maximizing the middle.
Almost. The other one is above, and we'll see that the gap here is not too bad, as long as we choose a good Q.
Last question about adversarial stuff. In that case, if your objective is minimizing the quantity on the left, then you can't use Jensen's inequality. Is that the right intuition? Like this only works if you're trying to maximize it.
Yeah. It only makes sense to maximize a lower bound to the function you want, because otherwise, yeah, it's not clear what the relationship would look like.
I guess if you want to go in the reverse direction.
It's very hard, unfortunately. There is QBOs, there is a bunch of, there is the ELBO and the QBO, and then there's a bunch of techniques that people have come up with, try to come up with upper bounds to these kind of quantities. But it's much trickier to get an upper bound than a lower bound. And intuitively, it's because if you just sample a few Z's, it's very hard to know whether you're missing some very important ones, which is what you would need to get an upper bound. While it's relatively easy to say that if I've seen so many Z's that have a certain amount of probability mass, there must be others. So it's always easier to get a lower bound than an upper bound, because the upper bound would require you to kind of rule out that there are many Z's that have a very high probability somewhere and you haven't seen it. That's the intuition.
Yeah, I guess this is related, but is there a way to quantify how tight the bound is?
Yeah. So there is a way to quantify how tight the bound is. So we know that for any choice of Q, you have this nice lower bound on the quantity we care about. This is the quantity we care about, and we got a lower bound for any choice of Q. If you expand this thing, you're gonna get a decomposition where you have this just the log of the ratio is the difference of the logs, and you can see that this quantity here is what we've seen in the last lecture being the entropy of Q. And so you can also rewrite this expression as the sum of two terms, the average log joint probability under Q, and then you have the entropy under Q. And it turns out that if Q is chosen to be the conditional distribution of Z given X under the model, then this inequality becomes an equality. So the bound becomes tight, and there is no approximation basically at that point. And so essentially what this is saying is that the best way of guessing the Z variables is to actually use the posterior distribution according to the model. So you have a joint distribution between X and Z that defines a conditional for the Z variables given the X ones, and that would be the optimal way of guessing the latent variables. The problem is that this is not going to be easy to evaluate, and so that's why we'll need other things, but this would be the optimal way of choosing the Q distribution. And incidentally, if you've seen the EM algorithm, that's what you need in the E step of EM. And there are some very close connections between EM and what we're doing here. Some says that's the best way of inferring the latent variables is to use the true posterior distribution.
Originally we had a Z and we were going to X, but if you also need to go from X to Z, then you have the cycle, right? Like how do you consider the computational graphing this way?
Yeah, so essentially what this would require you is to say, given an X, if you have a VAE, you would have to figure out what kind of inputs should I fit into my neural networks that would produce this kind of X. So you kind of have to invert the neural network, and you need to figure out what were the likely inputs to the neural networks that would produce the X that I'm given, which is in general pretty hard, as we'll see. But we can try to approximate that. Cool, I think we're out of time, so this is probably a good place to stop. What we'll see is then the machinery for training a VAE will involve optimizing both P and Q. And that's what we're going to see in the next lecture.